So it's a great pleasure to have Johannes Lange today in our CosKASI seminar. Johannes did his undergrad at the Free University of Berlin, followed by a master's degree in Heidelberg with exchange in UC Santa Barbara and Chinese University of Hong Kong. He then did a PhD at the Cavalry Institute in Santa Barbara. No, it was not the PhD. So he did the PhD at Yale.
Yes.
And then, then you went to UC Santa Cruz and to Stanford University, and he's now at the University of Michigan. And we're very grateful that you took your time today during your Thanksgiving holidays to talk to us. And please go ahead.
Yeah, thank you so much. Make sure everybody can see my slides.
Yep, perfect.
Okay, wonderful. Yeah, first of all, thank you so much for inviting me. It's really a great pleasure to be able to share with you some of our recent results, including a paper that we just submitted a few weeks ago, and that's not on arXiv yet. So I'm very curious to hear what you think. So generally, I will talk about probing cosmic structure growth with what we call full-scale cross-survey modeling of large-scale structure. And I'm going to talk about this in 5 broad parts. So first, give an introduction to cosmic structure growth and motivate why it is so relevant to studying dark energy. Then I'm going to summarize some recent findings from large-scale structure surveys, particularly those using gravitational lensing. And I'll talk about the possibility of what we call NS8 tension. And then I'm going to talk about one of our recent works on the lensing as low problem, what it could tell us about cosmology, but also possibly about galaxy formation physics. And then I'll present recent results from modeling the redshift space clustering of galaxies and what it reveals about the S8 tension. And finally, I'll talk about the recent paper that we just submitted, where we do a first joint full-scale analysis of both redshift space clustering and galaxy-galaxy lensing. So I just want to start by giving a very brief overview or a standard model of cosmology and motivating studying cosmic structure growth. So we have this very successful standard model of cosmology, whereby the universe starts out with a hot Big Bang. And in the first few moments of the universe, you have this period of rapid expansion that we call inflation. And this period eventually stops, but the universe continues to expand and cool down. Eventually, you have the release of what we call the cosmic microwave background, the CMB, which encodes a wealth of information about the early universe and can tell us about different properties of our standard model. After the release of the CMB, we enter what we call the dark ages, because the background radiation cools down and fades, but we don't yet have first stars. But over time, of course, by gravity acting, you have structures collapsing, you have formation of the first stars. Ultimately, this will reionize the universe, and eventually you end up with the universe that we have today, where you have all the galaxies and large-scale structure, and also where the expansion of the universe is dominated by dark energy. And so that model of cosmology is known as lambda CDM. Lambda stands for dark energy. It's what we think drives the accelerated late-time expansion of the universe. And it's called lambda here because for all that we can tell, dark energy is consistent with this cosmological constant that Einstein first introduced in his field equations. Similarly, CDM stands for cold dark matter. Cold because we think that dark matter has negligible thermal velocity. Dark because dark matter we think has negligible or no electromagnetic interactions with itself or other forms of matter, and we think that dark matter primarily interacts via gravity. Now, the standard model of cosmology is very elegant. It is able to explain a very large variety of observations using only a small number of tunable parameters. However, it is not very well theoretically motivated because we don't know what either dark energy and cold dark matter really are, and that's something we want to explore in the next 10 to 20 years. So for dark energy, of course, we want to know what causes this late-time accelerated expansion of the universe. Is it maybe that general relativity breaks down on cosmological scales, or there's some sort of new field, or maybe there really is just this cosmological constant in the field equations of general relativity. And similarly, for dark matter, if it is a particle, which is leading theory, we want to know what kind of particle theory would give rise to cold dark matter. And so in cosmology, we have this lucky circumstance that we have two very separate windows into the universe. So on the one hand, we have the CMB, which probes the universe, and was only a few 100,000 years old at a redshift of 1,000. And then we have what can be called the late universe, everything below redshift of around 10, let's say, includes large-scale structure, also includes local measurements of the expansion rate, and it probes the universe when it's a couple of billion years old. And so having these two separate windows into the universe at different times has allowed us to really stress test this standard model. And by doing so, we've uncovered potential cracks in the standard cosmological model. And one of those is the well-known Hubble tension, whereby the expansion rate that we measure in the local universe is slightly higher than what we would have expected by looking at the CMB and basically just fast forwarding to today. So this is commonly expressed in this H0 parameter. You can see there's a difference of around 10% in the expansion rate. And nowadays, this difference has reached a significance of around 5 sigma, so it's pretty hard to ignore. Now, in addition to this Hubble tension, we also seem to see hints of additional tension that can be called a growth tension, or also S8 tension, because it is commonly expressed in this S8 parameter, which is defined here in the bottom right. S8 is a combination of sigma 8 and omega matter. Sigma 8 is the amplitude of matter fluctuations on scales of 8 megaparsec, and omega matter is the amount of matter in the universe. And when you look at this S8 quantity, you can see that predictions from the CMB are around 5 to 10% higher than what we typically infer when we look at the local large-scale structure. And this is very important because cosmic structure growth and the amount of matter fluctuations is actually a very sensitive probe of dark energy. And to make this point, I just want to show a simple diagram comparing two different cosmologies. So it's on the left-hand side here. What we show is the linear growth amplitude. So basically, the amount of matter fluctuations normalized by the amount of matter fluctuations today. So by definition, it's 1 at a scale factor of 1, which is today. And we compare two cosmologies here. One is Einstein-de Sitter cosmology, where there's only matter and no dark energy. And the blue line is our standard cosmological model, known as CDM, that includes dark matter and also dark energy. The point here is that if you have dark energy, you need to form more structures at earlier times in order to arrive at the same amplitude today. And the reason is that as soon as dark energy takes over the expansion rate of the universe, this tends to slow down cosmic structure growth. And so the point I want to make here is that the presence and amount of dark energy has an important effect on cosmic structure growth. And so thereby, by studying cosmic structure growth history throughout cosmic time, we can constrain the amount and properties of dark energy. And so with that in mind, I want to just quickly summarize some recent findings from large-scale structure surveys with respect to growth of structure, and particularly those large-scale structure surveys focusing on gravitational lensing. So in gravitational lensing, we use the effect in general relativity that light is perturbed in the presence of some gravitational field. So this is a really nice cartoon here by Jesse Moore from the Dark Energy Survey. Let's assume we're looking at some far away galaxies. Then, in the absence of gravitational lensing and other complications, basically those background galaxies would be expected to have random shapes with random orientations. But now, if you place a foreground mass in between us and those faraway galaxies, then the presence of the gravitational field will deflect the light from the faraway galaxies as it travels towards us, and this will lead to subtle distortions in the apparent images of these background galaxies, particularly their shapes. So now their shapes will be preferentially aligned perpendicular with respect to the foreground mass distribution. And this is, of course, only a cartoon, but it really kind of shows what we typically measure in gravitational lensing. We measure these apparent coherent shape distortions of background galaxies. And by measuring that, turns out you're sensitive to this S8 parameter, this combination of sigma 8 and omega matter. And so nowadays, it's one of our leading data sets that we can use to constrain cosmology with large-scale structure. And we have different lensing surveys that measure the shapes of hundreds of millions of galaxies over large parts of the exoelectric sky, and basically give us maps of where we think the matter is in the universe. And so I really want to summarize the most recent results coming out of these lensing surveys, and the leading ones are the Dark Energy Survey, DES, the Kilodegree Survey, KIDS, and the Hypersuprime Chem Survey, HSC. And I present here the results coming from these cosmic shear studies. So let's start with the Dark Energy Survey, DS, on the left. Here are the constraints on S8 and omega matter. In yellow are the predictions from the Planck CMB analysis. And you can see the green contours show the results from the DES year 3 analysis. And you can see there's not really a strong tension between those two data sets, but you can definitely see that the DES analysis prefers lower values for S8 than what would have predicted based on the CMB. In and of itself, that's interesting, but not significant. But it becomes exciting once you look at the other lensing surveys and what they find. So for KIDS, which is in the middle, very similar plot, constraints on S8 and omega matter. In this case, the CMB constraints are here in red, and different other contours show different analysis choices for the KIDS data set. You can see they all prefer lower values for S8. And the same is true for HSC. So in this case, the CMB constraints are in blue, and the HSC constraints from cosmic shear are shown in red. And so it's really peculiar that you have these three independent lensing surveys that all point towards the possibility that S8 is actually lower than what we would have inferred from the CMB. And so that in combination makes this very exciting. And now, of course, we would like to this discrepancy to have a significance of at least 5 sigma to really claim confidence. So one strategy would be to just wait for better data, like the Verun Observatory in several years. But what I'm working on is how can we maximize the information content, the cosmological information content that we can extract from existing data. And one way that I approach this is by looking at a larger range of scales than what we typically analyze. So typically, when we analyze the large-scale structure distribution of the universe, is we concentrate on scales larger than a few tens of megaparsec. The reason for this focus on large scales is that on the largest scales, the universe is, or density contrast of the universe is close to linear. So you can make very accurate predictions for matter clustering from perturbation theory. And also the relationship between the galaxies that we see and the underlying matter density field is quite simple. You can, or relatively simple, you can describe it with a small number of bias factors. If you want to push down to smaller scales, then there are additional challenges you need to overcome. First, if you would push down to scales smaller than a few tens of megaparsec, the density contrast increases. And up to some level, you can still work with perturbative approaches, but eventually those will break down. In order to predict the matter clustering on scales of, let's say, 10 megaparsec or smaller, you need to run expensive n-body simulations of cosmic structure formation. If you want to push down to even smaller scales, at some point you also have to worry about the exact relationship between the galaxies that you observe and the underlying dark matter field, more precisely relationship between galaxies and dark matter halos. And finally, if you want to push down to scale smaller than a few megaparsec, you might also have to worry about, for example, what baryons are doing. So just one example, it's expected that AGNs expel large amounts of gas from the centers of dark matter halos, and that evidently affects the matter distribution on those scales. And the problem here is that just to what extent they do this and the amplitude of that is hugely uncertain. And so as you can see, if we want to push down to smaller scales, there are a lot of additional challenges that we need to overcome. But at the same time, if we're able to do so, we could potentially get much stronger constraints on cosmological parameters. That's something that several works have shown, and that's also something I want to convince you of in this talk. And so as a first application of all this, I want to talk about what's known as the lensing is low problem, which actually turns out to be closely related to this S8 tension. And so this lensing is low problem goes as follows. So let's assume, or let's take a cosmological dark matter only n-body simulation of cosmic structure formation that has cosmological parameters consistent with the Planck CMB analysis. And then you fit a galaxy halo connection model to predict or to reproduce the clustering properties of a set of galaxies. And if you do that, then it turns out you make very precise predictions for what the gravitational lensing amplitude around these galaxies should look like. And so that's what's shown on the right-hand side here from actually the TOES paper in 2017 that really defined this lensing as low problem. So just make sure we know what we're looking at. So the y-axis here is the galaxy-galaxy lensing amplitude. It's often expressed in this quantity here called delta sigma. It's basically a measure of the amount of matter within a certain radius from the galaxy. So you can see it's expressed as a function of the radius from the galaxy. And it's basically just a measure of, or the way we measure observation is by looking at how much galaxies are distorted or aligned perpendicular with respect to the lens galaxy. So you can see that these different lines here, they come from different models tuned to reproduce the clustering of luminous red galaxies in the BOSS-CMASS galaxies, BOSS-CMASS sample. And these different lines, they come from different studies, and they have used different models for the galaxy connection. They have fit into different clustering statistics. The point is that despite these differences, they make very consistent predictions to within like a few percent of what the galaxy-galaxy lensing amplitude should look like. But the lensing is low problem is that the actual measured lensing amplitude is lower than what we expect it to be by around 30%. And this discrepancy is most significant on scales below around 2 or 3 megaparsec, where the signal-to-noise lensing measurements is the highest. Now you can easily show this as possibly related to the S8 tension. If you were to assume a cosmology with a lower value of S8, you would naturally predict a lower lensing amplitude at fixed clustering. And so it would alleviate the S8 tension. But because we're looking here at small scales, we also have to worry about, for example, the impact of baryons, details of the galaxy connection, or also possibly lensing systematics, because these gravitational lensing measurements are very difficult. You're trying to measure very subtle distortions in the shapes of black-hole galaxies. We also want to make sure that our lensing measurements are robust. So let's talk about these things in the next few minutes. So first, details of the galaxy connection. One thing that people worried about for a long time is an effect called galaxy assembly bias. Now, typically, when we model the galaxy connection, we implicitly assume that the only property that determines how many galaxies live in dark matter halo, everything that determines that is the dark matter halo mass. But there's no reason to assume this. This might be that the number of galaxies also depends on, for example, when the halo formed. If that's the case, and that we call galaxy assembly bias, this will also affect clustering and lensing predictions. That's something that typically is ignored when modeling the galaxy connection and when making predictions for clustering and lensing. And so in this work from a few years ago, we're the first ones to analyze whether this lensing is low problem can potentially be alleviated with galaxy assembly bias. So the same exercise made predictions for the lensing amplitude at fixed clustering, but now take into account models that also have galaxy assembly bias. So especially on the right-hand side here, the predictions for different models normalized by the prediction from the standard no galaxy assembly bias model. And you can see that the red band is if you assume the standard modeling, which gives you very tight constraints on what lensing amplitude should be. But once you allow for galaxy assembly bias, which is shown by the blue and the green contours, you get a significantly larger range of predictions for the small scale lensing amplitude. At the same time, though, these are 95% confidence intervals. And so even in very extreme cases, you're only able to push down the lensing prediction by, let's say, 10 to 15%. And so by and of itself, galaxy assembly bias is probably not enough to fully alleviate this SA tension. What about baryons? I said that AGNs might expel large amounts of gas from the centers of dark matter halos. So we analyzed this in two very popular hydrodynamical simulations. So shown on the left-hand side here, these are predictions from the illustrious simulation, so dashed lines, and the solid lines are from the updated illustrious TNG simulations. And just different colors just correspond to different stellar mass samples of galaxies. The main point here is that, as expected, baryonic physics, taking this into account, is able to lower the predicted lensing amplitude by around 10% on smaller scales. So again, by and of itself, that's not enough to fully resolve the lensing is low problem. Now, more recently, there was a very exciting study also putting observational constraints on the amount of baryonic feedback, such as on the right-hand side here. The authors measured the Sunyaev-Sedovich effect around these Boss C-mass galaxies. And the Sunyaev-Sedovich effect basically probes the gas around galaxies, and thereby the authors were able to constrain empirically the amount of baryonic feedback and how it affects the expected galaxy-galaxy lensing amplitude. And so that's basically the difference here between the red solid and the blue solid line in the plot on the right-hand side. But the result is basically the same. You're not able to fully resolve this lensing is low tension with just baryonic feedback. So what about lensing systematics? There's a recent study that we published called Lensing Without Borders. Here we're using a really interesting approach where we combine the strength of different large-scale structure surveys. So we take a common set of foreground galaxies, in this case from the Boss survey, where we have a large number of LRGs with high-quality spectroscopic redshifts. And then we measure the lensing amplitude around them using different lensing surveys. And the point is that we're measuring this delta sigma galaxy lensing amplitude, which is a physical quantity. It should in principle not depend on which lensing survey you use to determine it. And so thereby, by comparing the different lensing amplitudes measured with different lensing surveys, we have a fairly model independent way to check the robustness of different lensing surveys and check for possible systematics. And so in the study, we compare these different lensing surveys, and that's what's shown on the left-hand side here. And the main upshot is that in this analysis, we find a pretty good consistency between different lensing surveys, meaning they agree to within the statistical and systematic uncertainties quoted for each of the lensing surveys. And so all this indicates that also lensing systematics are probably not the full story to explain this lensing is low problem. Now, in our most recent study on lensing is low problem, we reanalyzed this using the highest signal noise data that we currently have, which is SDSS. So the same exercise, we assumed Planck CMB cosmology, fit a model for the galaxy connection to the clustering properties, in this case of Boss-Low-Z galaxies, and then make predictions for the lensing amplitude and compare it to what we measure. The novelty of this work is that we do this for different samples of galaxies with different stellar masses, which then also probe very different underlying dark matter halos with different masses and different large-scale binds. So let's, for example, look at the left-hand side. So what I'm showing here is the ratio of the observed lensing amplitude to the one that we predicted based on clustering. And the different colors here are just the different galaxy samples with different stellar masses and by extension different halo masses. And different panels are just different ways to define the stellar mass. And the point here is that we get very consistent results between different galaxy samples, just showing us that there's no mass dependence to this lensing slow effect, and also arguing that we probably have modeling the galaxy connection under control. And also using these very high signal noise measurements, we also see that this lensing slow problem might extend to larger scales, so even scales above a few megaparsec. But of course, it's assuming that the SSS lensing measurements are robust. But all this just indicates that this lensing slow problem is a very interesting problem that can tell us something about cosmology, but possibly also about details of the galaxy connection and also baryons. And so in order to resolve this, it would of course be great to also have a different way to assess this as a tension, and that's what we'll talk about next. So we recently had an analysis where we infer cosmic structure growth, not using gravitational lensing, but rather using redshift space clustering. So what we're analyzing here is the clustering of galaxies in redshift space. So we measure the amount of galaxy pairs separated by a line of sight direction, r pi, and perpendicular direction, rp. And in principle, there's no preferred direction in the universe. So in some sense, you would expect this plot to be completely spectrally symmetric. But you have redshift space distortions. Because of the peculiar velocities of galaxies, the measured redshift is affected, which then affects at what distance we place each galaxy based on its observed redshift. And this has two main implications or effects. So the first one on small scales is the so-called fingers of God effect. So basically you have, for example, clusters where you have galaxies zipping around in the gravitational potential well, they have large velocities, and due to redshift space distortions, this leads to a smearing out of the cluster along the line of sight direction. That's basically what you can see here at small separations. And then on large scales, you have what's called the Kaiser effect. Basically, the galaxies tend to fall towards overdensities, towards each other, and that leads to a squashing of the two-point correlation function along the line of sight direction, r pi. That's also what you can see here. And so basically what we're going to do is we're going to measure this Kaiser effect, which tells us about the infall velocities of galaxies, and by extension tells us about the amount of structure in the universe. And this is nothing new, but what we're doing here for the first time is we're analyzing this down to much smaller scales than what is typically done in a fully cosmological context. So other works would typically analyze these two-point correlation functions on scales larger than 30 megaparsecs, so basically extending outside of this plot. But you can see there's a lot of information even on scales smaller than that. And so that's what we're going to do. In order to do this, to get full cosmological constraints, we can't just run a single simulation that, for example, would probe the Planck cosmological parameters. Instead, we need a suite of cosmological simulations. And this work, we use the MLIS simulation suite. And I believe Sarah Fisher gave a talk here a few weeks ago where she also talked about the simulation suite. So this is a suite of 40 simulations that have different cosmological parameters. On the left-hand side, you can see the parameters that they probe. Basically, each point is one of the simulations, and they probe basically the combined 4 sigma contours and with a combined analysis of CMB, BO, and supernova. Each simulation has 1,400 particles, or 1,400 cubed particles, and a side length of around 1 gigaparsec. Now, with this volume and resolution, it's basically an ideal simulation set to analyze luminous red galaxies, like the one that we have in BOSS, LOW-Z, and CMASS. Now, there's still some details involved on how you can use such a small number of simulations to get full cosmological posterior constraints. And there are 2 papers that I list there that explore this in detail or present techniques, how you can do this. But I don't want to focus on this here, but rather tell you what we find in terms of cosmology. So we analyzed this using a very standard galaxy connection model. It's based on this halo occupation distribution approach, HOD. We parameterize basically the number of galaxies living in dark matter halos as a function of their mass. But of course, then we also allow for galaxy assembly bias by this Legro HOD approach. And then we also model velocity and spatial bias of galaxies within dark matter halos. So for example, satellites are assumed to follow an NFW profile, but we allow their concentration to be different than that of dark matter in the same dark matter halo. And similarly, we have additional central and satellite velocity bias parameters. And then we analyze the BOSS LOW-Z data. So we measure this isotropic 2-point correlation function, which is typically expressed in these multiple moments. In this case, we analyze the monopole moment, which is in yellow, the quadrupole moment in pink, and the hexadecapole moment in purple. And we have 2 galaxy samples at 2 redshifts. You can see the measurements here, and the line that goes through that is our best fit model. And you can see it's able to explain both observation data sets quite well, and you get a reduced chi-square of around 1. And so the main result of this paper are then the constraints on the cosmic structure growth rate, which is F sigma 8. And yes, on this plot, we compare constraints on F sigma 8 in our work, which is shown in red, against other large-scale structure analysis on redshift space distortions that focus on large scales only. So these are the other error bars, as well as the constraints or predictions from the Planck CMB analysis. And so those Planck CMB constraints are shown with the blue line and bands. So there are 2 main takeaway points. The first one is that we are presenting some of the most stringent constraints on F sigma 8 thus far. That's because we analyze the redshift space clustering down to much smaller scales than what we typically analyze. In fact, we show that for the same data, if you're able to push analysis from, let's say, 20 megaparsec down to 1 megaparsec, get an improvement of around a factor of 3. And so therefore, we have tighter constraints, even though we actually only use a small subset of data that is available. And the other point is that our results are fairly consistent with the Planck CMB predictions. So you can see the low redshift data point actually agrees perfectly. The high redshift data point is around 2 sigma lower than the Planck prediction, which is interesting, goes in the same direction as the S8 tangent. But again, by itself, that's not really sufficient to claim anything.
Minutes?
Mm-hmm. Sorry, is that a question?
No, I just said 10 minutes.
Okay, good. So that leads me to the last point I want to talk about, some of our recent analysis, where we combine these 2 previous topics. So we jointly analyze redshift space clustering as well as galaxy-galaxy lensing. And so for this work, we also produced new galaxy-galaxy lensing measurements using state-of-the-art lensing datasets. So the recently released DES Year 3 analysis, or data products, as well as the KITS 1000 lensing catalogs. And we now analyze 3 redshift slices for Boslow Z, which basically allows us to analyze more galaxies. We compare here the lensing amplitudes for DS, KITS, and SDSS. SS continues to be the highest signal noise lensing measurement, but DS is getting close, and importantly, DS and KITS are thought to be much more robust, to have much lower systematics than SDSS, so we're having much more confidence that those results are in fact accurate. And so before applying this to real data, we performed some mock tests. So we create some mock galaxy catalogs where we know what the input cosmology is and make sure that we can recover the true input cosmology. Those mocks are based on subrate abundance matching, and they were analyzed with the same pipeline as the real data. And so the main plot here is on the left-hand side. The input cosmology is shown by the yellow star and yellow dashed line. And you can see the different colors here, showing various choices for what we analyze. So purple is the combination of project clustering and galaxy-galaxy lensing. In that case, we're not sensitive to redshift space distortions, but only to galaxy-galaxy lensing. And the blue contours if you analyze only redshift space clustering and no lensing. In that case, S8 constraints come primarily from redshift space clustering. And finally, the red contours are if you combine both redshift space clustering and galaxy-galaxy lensing. So luckily, you can see that in all cases, we're getting accurate cosmological constraints, particularly on S8. And the cosmological constraint power is the highest when we combine redshift space clustering with galaxy-galaxy lensing. And so then we apply this to the actual data. And so I said we have 3 redshift slices for Boslow Z. And we also choose to analyze galaxies in the northern and southern galactic cap separately, because they have slightly different photometries. So we overall have 6 different galaxy samples. And these are the measurements and the best fit models. So on the left-hand side are the redshift space multiple moments. Right-hand side are the galaxy-galaxy lensing measurements. 2 points I want to make here. First, for galaxy-galaxy lensing, we actually exclude scales smaller than 2.5 megaparsec, because for this work, we don't have a model for baryons, and those scales are affected by the presence of baryons. And secondly, we're able to fit all these observations, these are 180 data points, very well, reduce chi-squares around 1. And so this all looks very good. And so what are our constraints on S8? That's what we can see here. I show the constraints for different galaxy samples and different choice of observables. Left-hand side is we only analyze redshift space clustering. Middle is if we analyze project clustering and galaxy-galaxy lensing. And right-hand side is we combine those two, so redshift space distortions and galaxy-galaxy lensing. And in each panel here, different colors correspond to the different individual galaxy samples, so 6 ones. And the black solid line is if we combine all the 6 different samples. And the point here is that there's very good consistency between individual galaxy samples and also between different statistics. So for example, if we infer S8 only from redshift space clustering, we get results that are very consistent with those that we get when we analyze the project clustering and galaxy-galaxy lensing. And so what I want to summarize here for this work is that this is the first joint full-scale analysis of both redshift space distortions and galaxy-galaxy lensing, and also the first full-scale analysis with cosmological analysis with DSY3 and KITS 1000 data. And we find different samples and probe consistent results on causal structure, particularly S8. And this leads to some of the tightest constraints on S8 produced thus far. So where does it leave us at? So the left-hand side is comparing different results on S8. You can see the Planck speed predictions here are shown in blue. and they go all the way to the bottom just to have a point of comparison. The yellow points are the cosmic shear results that I presented at the beginning of the talk. You can see they all lie below the prediction from the Planck-Simbi analysis, and you can see different studies here with different choice of observables. And our flagship result is basically here, the gray star, which is coming from combining redshift space clustering and galaxy-galaxy lensing. And our results are, because we analyze small scales, we're fairly independent of these other cosmic shear studies, but we also find a result that is very consistent with these cosmic shear studies. So we find around a 2 to 2.5 sigma tension with the Planck CMB predictions. And so that's what we've done so far. I just want to spend a few more minutes talking about some of the future work that we're planning to do. One thing I just mentioned is that for lensing analysis, we don't probe scales smaller than 2.5 megaparsec because we don't have model for baryons yet. But something that we are currently working on is to also include a model for baryons and constrain this using these observations of the Synav-Sadovich effect. So we would also use the overlap of the BOSS galaxy survey with the footprint of the Atacama Cosmology Telescope ACT, and then measure this thermal Synav-Sadovich effect and constrain models for baryonic feedback. And so basically then by jointly modeling redshift space distortions, galaxy-galaxy lensing down to very small scales, and also Synav-Sadovich effect, we hope to get even better constraints on cosmology with existing data. But of course, something that of course a lot of people are excited about is the upcoming dark energy spectroscopic instrument, DESI. I don't talk about this too much here, but it's successor to BOSS and SSS, and will map the extragalactic sky with a much higher redshift density than what was possible with SDSS. And so from that alone, we already expect much better cosmological constraints, and it's going to be really exciting, especially also given that DESI has very large overlaps with the HSC survey and the KITS and DS and ACT surveys. And so in the future, we hope to really perform these full-scale cross-survey multi-wavelength studies to really maximize the cosmological information content that we can extract from large-scale structure surveys. And so with that, I'll leave you with my conclusions and be happy to take questions.
Thanks a lot for this clear, instructive talk and for keeping in time so well. So if you have questions, please use the raise hands reaction or just unmute. While everyone's getting their thoughts, so I asked the first question. So on slide 10, you had KITS contours, which were CF versus QE, which I guess they're just different estimators for the same data.
Mm-hmm.
Actually, I was thinking that they look like intention similar as with the Planck, but actually now that I look at it again, the tension doesn't look too big. It's just that. Oh no, I'm looking. So yeah, so somehow they also look a bit at tension. Is that?
Mm-hmm. I mean, KITS and Planck?
No, just KITS with KITS, where the CF and the QE.
So the red one is the Planck, and everything else looks pretty consistent with each other. Right in the middle, are we talking about the same thing? Just want to make sure.
Oh no, on the right, the one.
Ah, that's HSC. Okay, sorry.
Okay, but it says KITS CF and KITS QE.
Oh, this one. Oh, good question. I actually don't.
Oh, is that something that
I don't know details about
I also see that it's KITS 450, so maybe that.
Yes, that's also KITS 450. So it's updated since then.
Okay, yeah. So maybe I was into. Christoph has a question.
Yes, hi Johannes. Have you ever looked at the possibility of using peculiar motion data to improve lensing estimate, because there are lots of overlaps with the sigma 8 estimates and similar things. So yeah.
So just make sure that I understand correctly. Do you mean use peculiar velocities to improve lensing measurements, or to use peculiar velocities in combination with lensing measurements?
In combination.
Yeah, that's something that's certainly very, very interesting, and certainly something that should be explored. I think one small issue might be that for peculiar velocities, you're probing really, really low redshift. And for those, the lensing kernel is not very efficient. So I don't know, you get like very good lensing measurements for really, really low redshift galaxies.
Yeah, the redshift limit is like 0.1.
Possibly. Yeah, that's certainly something that would be very interesting to explore. I'm not aware of anybody doing this, but that's definitely a possibility. Yeah.
Thanks.
So no one else has raised their hand, so I'll ask another stupid question. So on slide 14, you showed two different contours for the galaxy assembly bias. Are these different models, or what's the difference between those?
Yes, these are two different models. Basically, we're modeling galaxy assembly bias by allowing the number of galaxies to depend on one additional halo property in addition to halo mass. And I'd have to guess here, but one of them is halo spin as a secondary parameter, and the other one is halo concentration as a secondary parameter. You can see they give slightly different ranges for the predictions. Does that make sense? There are two choices for a secondary parameter that determines the number of galaxies per halo.
Would it make sense to combine the two, so to have like a 3-parameter model?
Sure. You could certainly also make this, or you could include a tertiary halo property as well. That might also affect things. I don't think they would just directly stack. I think it would probably get a contour that looks slightly larger than the green one, probably not dramatically larger. Is my guess.
It would not blow up the error like.
No.
So yeah,
I don't think so. I haven't tested that yet, but I would be very surprised.
Yeah. So I still wouldn't explain the too low lensing signals.
Right.
Okay. Anyone else has any questions? Then on slide 27, you said that you had for this for the plotted front, you didn't have a barrier model. So I probably didn't get why that was.
Right. So may I just gloss over this too quickly? So the right-hand side shows the lensing measurements. So the galaxy lensing measurements. And for those, we do not analyze, we don't use for the cosmological constraints scales smaller than 2.5 megabars. And that's because our modeling is based on these annulus dark matter only simulations. So they don't include any models for baryons, and we also don't put anything in after the fact. And so therefore, our model does not include baryons and does not include the possible impact that baryons would have on the lensing measurements on those small scales. And so therefore, this could lead to possible biases if we would analyze those small scales, their lensing measurement. And so therefore, we exclude it, at least for now.
Okay, that makes sense.
But in the future, we're currently working on analysis. We do have a model for how baryons affect the small scale in the signal, and also a consistent model for also how this would impact the measured synapse-Dobich effect. And then if we jointly analyze lensing, clustering, and a synapse-Dobich effect, then we can directly constrain the amount of baryonic feedback and then also really make use of those small scales.
Okay, cool. I guess you probably mentioned that, but I somehow missed it. Are there any other questions? If not, we can close the official part of the seminar here.